Welcome back! In this lesson, we'll discuss different types of vector databases you can use. We'll discuss the pros and cons of each one, and the main reasons why I chose to show Pinecone in this course. You'll see that each option has its own unique advantages, and no single solution is perfect. Additionally, these solutions are continually being enhanced and updated, with new versions of databases launching as I record this. It certainly is an exciting time for vector databases. So let's start with Pinecone. Pinecone was founded in 2019 by Edu Liberty, a former research director at AWS and Yahoo. It was initially developed to improve applications like recommendation systems and spam detectors. Pinecone is a managed vector database designed to make building and scaling similarity search applications easy. It's known for its simplicity and robust performance. Regarding strengths, Pinecone stands out as a fully managed service, ensuring you don't need to handle infrastructure management or scalability issues. In addition, Pinecone scales automatically and maintains high performance even with large datasets. And with an intuitive API, Pinecone makes it easy for developers to integrate and use. On the flip side, it suffers from limited customization opportunities. Being a managed service, Pinecone offers less customization compared to self-hosted solutions. Additionally, while offering convenience, Pinecone can be more expensive than self-hosted alternatives, especially at scale. Great! So how about Milvus? Milvus, founded by Charles Sheeha, founder and CEO of Zilliz, is a cutting-edge vector database specializing in large-scale similarity searches. As an open-source platform, Milvus is highly regarded in the AI community for its versatility and powerful indexing capabilities. Zilliz also offers a cloud solution known as Zilliz Cloud. Regarding strengths, Milvus is entirely open source, allowing for extensive customization and integration. What's more, it's highly scalable. Milvus supports a variety of indexing methods to optimize search performance and is designed to handle billions of vectors. It can also combine traditional and vector search, enhancing its application range. And what about weaknesses? Well, if you're a beginner in vector databases, you might get overwhelmed by the complexity of this solution. With its extensive features comes a steeper learning curve. Furthermore, learning how to optimize the database for your own needs may require more expertise. And we must also mention that being self-hosted, you need to manage your own infrastructure, which can add complexity and cost. All right. Our next solution is called Weaviate. Founded in the Netherlands in 2018 by Bob van Lout and his team, Weaviate is designed as a powerful, scalable, and user-friendly vector search engine that enhances searches and automates classification through integration with ML models. Weaviate is an open-source vector search engine that combines vector search with a graph database, enabling rich data models and contextual searches. One of its key strengths is integrating graph database features with vector search, enabling semantically rich contextual searches. It also supports automatic data vectorization through pre-built machine learning models. Weaviate also offers GraphQL and RESTful APIs for easy integration. And how about Weaviate's weaknesses? As a newer player, Weaviate may lack some advanced features in more established databases, although it could catch up in the future. Another potential drawback is that the combination of graph and vector search can sometimes lead to performance trade-offs in large datasets. Fourth on our list of comparisons is Quadrant. Quadrant, a recent addition to the vector database sector, was developed by Mikhail Belyayev and his team, who established the company bearing the same name. Launched in 2020, Quadrant's mission is to deliver a robust, open-source vector search engine optimized for high performance and scalability. A key strength of the database is performance optimization. It focuses on high throughput, handling numerous queries per second, and low latency in vector searches, significantly reducing the time to obtain results. Additionally, Quadrant allows custom indexes to be created that are tailored to specific data characteristics. This means that users can choose from or combine different indexing strategies to fine-tune the database and enhance search performance. Another advantage is that Quadrant has a few valuable data management features. For example, they offer payload filtering, which allows you to include filters in the vector search queries. So alongside your query vector, you can specify different attributes of the vector like color, size, or anything relevant to your search. Quadrant also supports ranking by custom logic, so your results can be ordered based on your own criteria, not just similarity. You could order articles by publication date, length, or other metrics. But with these features comes a more complex setup, which might be difficult for newer users. You might require time and expertise to fine-tune the database for the best performance and the more advanced features. A potential drawback of this vector solution is it's still newer in the market. And while this doesn't necessarily mean it's inferior, it might lack community support and extensive documentation found in more established options. Okay. I've given you a brief overview of the most popular vector databases. But as mentioned, this increasingly important topic is seeing new solutions emerge in the market. For example, Oracle has also introduced its own vector solution with AI. But what does that mean for you and your vector database needs? As you've seen, each vector database has its own set of strengths and weaknesses, tailored to different needs and scales. Understanding these nuances enables you to make informed decisions to enhance your projects with the most suitable vector database technology. I've chosen Pinecone for its ease of use, intuitive interface, and powerful capabilities. It efficiently supports many vectors and vector search. You're welcome to explore other options and find what best suits your needs. When you're ready, join me in the next lesson where I'll walk you through registering on Pinecone and creating your first index. See you there! Hi and welcome! It's time to move towards the practical part of this course. We've discussed the pros and cons of popular vector solutions and have landed on Pinecone. In this lesson, we'll do an intro, a registration to Pinecone, and a walkthrough of their site. We'll also create our first ever index. Let's start by registering to Pinecone, which is fairly simple. Visit pinecone.io and click Sign up for free. You're not asked to come up with a password. Instead, each time you log in, you receive a code to enter for verification. I love that. It's much easier than managing countless passwords. Okay. You'll now need to fill out some information, including the organization you work for. The reason for that is that Pinecone can support multiple organizations for a client in their workspace, which you'll see in a minute. Good. With our registration complete, let's take a look at the workspace. At the top, the Pinecone logo links back to this workspace when clicked. Beside it, we see the name of our organization, and if I click on it, a drop-down menu appears. As I only have one organization entered, I cannot make the switch, but if you do, this menu enables you to navigate between them. Next up, we have our projects, which are the starter projects for me. I'm using Pinecone's free version for this course, which is called a starter project. Keep this in mind because we might use that detail when we try to connect to Pinecone later. Next, you can see Pinecone's different price plans if you go to Settings. If you have a starter plan, the free version only allows 5 indexes, 1 project, and 1 workspace. But for our purposes, this will be enough. All right, what else? Let's go back to the beginning. From the Manage panel on the left-hand side of the page, select API Keys. Here, we can find and manage our API keys. We have a default one and can create new ones if needed. When we start writing code, we'll need those to connect to the Pinecone server and index. Keep in mind that these shouldn't be shared with other users. That's why if a key has been leaked, you should delete it from this menu and create a new secure one. Good to know. To end this first practical lesson, let's create our first index. You can consider an index as a vector store enhanced with extra features. When it comes to creating a new index, the process is straightforward and user-friendly. And the entire platform feels like that. Incredibly sleek and fast. It's a pleasure to use. We need a name for our Pinecone index. I'll choose the simple title My Index, as I'll frequently refer to it throughout this course and want an easy-to-remember name. Okay, what else? Apart from the name, we must specify the number of dimensions. Each vector we create will have the same number of dimensions, and their dimensions must equal the number we put here. For illustrative purposes, I can enter 2 or 3, which means that each vector will have 3 dimensions. In reality, this number will depend on the embedding algorithm you're using and will most definitely be larger. Excellent. You can see that the metric for the closeness of the vectors is cosine, and I'd like to stick with that, but feel free to choose dot product instead if that's more relevant to your task. And voila! We have our brand new index ready. So far it's empty. I'll show you soon how to fill it up with your own data. First though, we need to connect to the Pinecone vector database with the help of Python. That's why we'll be switching up to Jupyter Notebook. I'll see you in the next lesson, and thanks for watching. Hi again. We've acquainted ourselves with the Pinecone I/O. Now it's time to get a bit more technical and learn how to connect to and manage vector databases using Python. First, import the necessary libraries. If you have not installed some of them before, you'll need to do so beforehand. You can do that via the Anaconda prompt using the pip install command. In addition to setting up the libraries, you'll also need to create a file called .env, short for environment. To connect to the Pinecone server, we must provide the API key from our previous lesson and specify our environment. We also need to specify the environment. As mentioned, we're using Pinecone's free version, so our environment is GCP-starter. You could put these 2 strings as parameters directly in your code. But I strongly discourage that because it would leave your code too vulnerable, and someone might get your API key. That's why we'll include a separate file to protect our code instead of that method. This also means that if some of the information here gets compromised, we may change it in the file without changing our code, making our code reusable. I've stored my .env file in the same directory as my code, which is done for convenience and to avoid specifying its directory path in the code. Okay, great. Returning to our code, we need to access this file in Python by importing 2 functions, find and load, from the .environment module. These functions do precisely as their names imply. They help us find and load an environment file. Good to know. In the following line of code, I'll call the load function and use the find function as a first argument. The override parameter is set to true, which basically means that each time we run this code, if there is a new version of the file, we'll use the new version. So far, so good. We have everything necessary to create a new Pinecone object. The only 2 things we ought to specify at this stage are the API key and the environment. You've seen where they are in the file. I'll use the operating system module and get the environment getEnv function to fetch them, specifying the names I assign to the API key and Pinecone environment. Now let's run the cell. Excellent. Let's call the listIndexes method to check that it has worked. We receive a list of indexes. In this instance, the list includes only the my index we created in our previous lesson. If you didn't create an index, you'll receive an empty dictionary as output at this stage. Instead, we obtain some useful information, such as the indexes' names, their dimensions, and similarity metrics. All right, we've successfully connected to the Pinecone server. In the next lesson, we'll learn how to create and delete indexes directly in Python. See you there. Welcome back. We've seen how to create and delete an index on the Pinecone platform. Since we'll be doing most of the work on our projects in Python and Jupyter, it's worthwhile knowing how we can manage the indexes directly in our code. With that in mind, let's create an additional index. I'll create 3 variables we'll need: the index name, the number of dimensions we'll have, and the similarity metric we'll be using. I'll rely on the same values we've had so far. All right, as you know, we already have an index by the name myIndex. So as a good practice, when creating a new index, we ought to check if an index with that name exists. If so, we delete it first. This can be achieved by a simple if statement, where we check if the name of the index we wish to create already exists on the Pinecone server. To check that, we'll use a list comprehension, iterating over the indexes that we currently have. At first glance, this code might seem complex, but it's actually quite straightforward. The listIndexes function call retrieves the indexes currently managed by Pinecone. What we get back are index objects. We iterate over each index from the list and retrieve their names. So if we find a match for the index name, we can delete it. You know what? Just for clarity, I'll add 2 print statements so that the user knows what's happening at each stage. If we have a match, we'll output index successfully deleted. Otherwise, we'll see no matching index found. I'll also use the fprint capabilities in Python to add the name of the index to the output. To do so, I'll add the name in curly brackets like so. And I'll use the same template for the second print. Now, run the cell and see the result. Excellent! We've successfully deleted our original index. But let's double check by showing our index list again. As you can see, we get back an empty list after we deleted our index. So if I rerun this cell, I'd expect to see the text saying that the index wasn't found, and that's precisely what we get. Great. Now let's create a new index by employing the createIndex function. To do so, we should specify a few parameters, starting with the index name in the brackets. Once more, we'll use the parameter we created earlier, and we'll do the same for the dimensions and metric parameter. Creating an index is cleaner using this syntax because you can easily change the parameters of your index. Of course, you can hard-code them if you wish, and that's what I'll do with the last parameter I write in the code. I'm using the exact specifications we saw on the Pinecone site. Since I'm using the free trial version of Pinecone, I cannot use some of the available cloud or region options, so I'm sticking to this to be safe. You're welcome to add your own specifications at this stage. And with that, we're ready to run the cell. Cool! Let's call our listIndexes function once again to confirm we've successfully created the index. Indeed, for your next exercise following this lesson, create another index with 1,536 dimensions using a different similarity metric. After you're done, join me in the next lesson where we'll upload data to our newly created vector databases. See you there, and thanks for watching. Welcome back. Hopefully you've had a chance to create the second index from the homework task as I've done here myself. If I recheck the list of indexes, I can see that we now have 2 entries here as expected. We've learned how to connect to the Pinecone server via API and manage indexes in Python. Now it's time for the more crucial phase, populating the databases with our data. This process is called upserting, a term that combines update and insert into a portmanteau. I'll be using this verb throughout the rest of the course, but know that it simply means that we're updating any existing data if a specified vector already exists in our store, or inserting new rows if the vector doesn't exist in our Pinecone database. Okay, first we must create an index object to specify which index we'll be using. The syntax here is fairly straightforward because we're using the index class. To create our object, we simply need to specify the name. I'll go with our first index. So far, so good. Now, the simplest syntax for upserting our data is to create a list of tuples, each with an ID and the value of the vector. Let me show you an example. I'll call the upsert method on the index and create a list. Inside it, we'll add a couple of values. We'll begin with a simple example and only include a few values in our first index. If you recall, it had only 3 dimensions, which means that we'll need to input 3 values. This is just for test purposes, so the data can be anything you want. In my case, I'll be using animal names with 3 values, the number of legs, wings, and tails. After running this cell, I get a message that I've successfully upserted 5 vectors, precisely how many items we added to our list. Let's go to Pinecone to make sure that everything ran smoothly. I'll hit the refresh button and voila! Our vectors are ready to be used. As you can see, we have the score between the items, which shows us how similar they are, according to our similarity measure. For this index, remember we opted for cosine similarity. Let's try measuring how close the dog vector is to the rest using the Query by ID option. I'll input the dog ID in the relevant field and click the Query button. This will give me the top 10 closest results from our query. Alright. Unsurprisingly, dogs, elephants, and cats are a complete match, as they have the exact same number of legs and tails and share a lack of wings. And since our database contains only 5 values, our top 10 is only a top 5. We'll see, though, that a mantis is deemed closer to a dog than a chicken. I'm not sure biologists would agree with that assessment, not due to any shortcomings in the vector database or similarity measure, but because of our data's limitations. In hindsight, when examining our vector data, we realize that we've omitted crucial details about the types of animals we're storing in our data, such as the genus or family of animals. Without such information, the similarity metric cannot attribute or judge those types of similarities. We'll explore the significance of robust data later in the course. Meanwhile, I hope you're starting to appreciate the advantages of vector databases. If we wish to continue with our animal example, we could create an index with more dimensions and include more intricate information about our vector data. Suddenly, dimensions in the realm of 700 or 1500 don't seem that strange when considering how much information you can convey about your data using different dimensions. Excellent work so far. For homework, you'll create vector embedding including metadata. In the next lesson, I'll show you how to upsert data using an embedding algorithm. See you shortly. Thanks for watching. Welcome back. We've made initial progress on managing indexes and upserting data. In this session, I'll show you how to upload a large text dataset and embed it to upload to Pinecone. I'm using one of Hugging Face's text datasets, which is used for training algorithms. But I wanted to show you how the vector solutions scale when we have a large amount of data. We start by examining the Fine Web dataset, which includes over 15 trillion tokens of English web data sourced from Common Crawl. You can find more details on the Hugging Face website, where you can see different versions of this dataset. You can use a sample of the data rather than the complete set. Mind you, this is still 10 billion tokens, so we'll see how we deal with that. Let's switch to the dataset card to see an overview of what the data looks like. As you see, you have the text, the ID, and the URL from which it was taken. It also features a date and has a language score. You'll see the text expand if you click on a data point. Various text lengths are included here, making them suitable for our database. Okay, let's return to our Jupyter notebook, where I've set up a new notebook and included the initial imports. Now, let's load our dataset using the load dataset method and specify that we're looking for the Hugging Face hosted Fine Web data. I'll opt for the sample of 10 billion tokens and use the split on the training data. As we've already mentioned, this may take a while to complete because this is a large data set. But once this is done, we can check what the variable contains. It contains an iterable data set with the same columns we've seen on the Hugging Face website. An iterable data set, helpful in managing large data sets, allows us to access data through an iterator, like a for loop, without storing the entire dataset on our computer, significantly reducing memory usage. So far, so good. In the next lesson, we'll choose an embedding for our data and upsert it to Pinecone. See you there. Hi again. We've successfully loaded our data with the help of Python. Now it's time to convert our data into vector form, which means that we must find an embedding algorithm. I'll talk about embeddings more extensively later in the course. Right now, I'll only briefly touch upon why one is required. Embedding is the process of transforming our text data into vector form. There are different ways to do so and other algorithms which have been implemented for that purpose. For this lesson, I'll use this general embedding algorithm, which has the advantage of being relatively fast. You'll see later that this wouldn't improve the speed significantly when working on such a large dataset. Okay, you already know what we need to connect to the Pinecone server. I'll quickly write up the necessary code, after which we can access our existing indexes. Good. As you can see, we have two different indexes already that we've created in previous tutorials. For this lesson, I'll create an additional one, which I'll name text. You've already seen me use the createIndex method, so nothing's new here, except for the dimensions count. Unlike our previous vector databases, we can't simply write any dimension number we like here. Instead, we must adhere to the number of dimensions used by our embedding algorithm. As you know, during the embedding process, all original data is transformed into a vector with n dimensions, and each vector in our data has the same number of dimensions. The correct number for this algorithm is 384, so you could hardcode this. However, using this method improves reusability and yields better results. Okay, let's connect to the index in question, called text, with this piece of code you've also seen. After that, we're ready to embed our existing data and upload it to Pinecone. First, we'll create a list of vectors that we'll upload to Pinecone. As you know, this is the accepted way of uploading vector data. Our list is initially empty. We'll add vector data to it iteratively. We'll use a for loop and iterate over the items in our dataset. Remember that we're using an iterable dataset, but in essence, we're fetching a row of the data with each iteration. We'll need to get the text itself. In order to achieve that, we require the text column of the item. Then we'll need the ID, and let's also add the language. Then we'll encode this text and transform it into an ND array because this is required for the upserting later. At this stage, we could add some metadata elements. For now, I'll simply add the language and you can experiment with loading different parts of the data as metadata later. Following the metadata, we can simply add our newly created embeddings, ID, and metadata to our vector list. Okay, what's next? With the for loop done and dusted, we can start upserting our vectors. We'll create batches of size 1000, which shows how many items will be processed simultaneously. When I enter the for loop, I'll iterate through the list, starting with the first element and proceeding in steps of 1000 until the end. Okay. In the batch variable, we'll store a list with vectors to upsert, starting from the current item to the batch size, taking that slice of the list. We're using the batches technique to speed up the process of upserting the data. You can experiment with different batch sizes and see which is optimal for your computer. Keep in mind that having too large of a batch size might be overwhelming for your memory, so there is a trade-off. Then, finally, we upsert the vectors from the current batch to the database. Okay, now before you run this piece of code, let me briefly explain a potential drawback. This code takes a really long time to execute on my machine because the data is so large. Depending on your device, you might find it easier or more difficult to execute this code within a reasonable time frame. That's why, instead of uploading the whole dataset, I'll take a subset of 10,000 entries which will be taken at random. That way I can show you the whole process and still have code that doesn't run all day. I'm adding this code to our for loop to ensure we only take this small subset of data, not the entire set. Essentially, we're introducing a condition to terminate the for loop once the subset size reaches 10,000. That's fairly straightforward in terms of code. You'll notice that as soon as the data gets a little bulkier, the embedding and upserting process starts getting a lot slower. So sometimes you can't afford to upload such large amounts of data at once. That's why in the next section, we'll use a small dataset for convenience in our case study. Okay. Now let's check if everything has gone according to plan. Switch over to Pinecone. In my case, I'll need to refresh the page. And there it is. The text dataset is completed with our new entries, which is great news. Explore the data in more detail here, examine the IDs and metadata, and evaluate if this is the best solution to upsert the data. You can tackle that after the lesson and take your time. In our next section, we'll start working on our case study related to semantic search. See you soon. Thanks for watching.